What if the universe is not the same in every direction? For decades, modern cosmology has rested on one powerful assumption. No matter where you look, the universe should appear roughly uniform on the largest scales. No center, no edge, no preferred direction. But when scientists mapped the oldest light in the cosmos, the cosmic microwave background, they noticed something strange. Some of the largest patterns in the early universe appeared to line up, not randomly, not evenly, but almost as if the universe had an axis, a hidden direction. And because this alignment seemed so strange, so uncomfortable, and so difficult to explain, scientists gave it a name that sounds more like science fiction than cosmology: the axis of evil. But what does that actually mean? Is this just a statistical coincidence? Is it contamination from our own galaxy? Or is the universe trying to tell us something about its structure that we still don't understand? Because if this axis is real, then one of the deepest assumptions in modern science may not be as solid as we thought. The universe may have a hidden direction. In this video, we're going to follow one of the most unsettling puzzles in modern cosmology. First, we'll look at the oldest image of the universe ever captured, the cosmic microwave background. Then, we'll see why certain patterns in that map disturbed scientists so much. We'll explore the so-called axis of evil, the strange cold spot, and why these anomalies keep appearing in discussions about whether the universe is truly random. And by the end, we'll ask the question that makes this mystery so powerful. If the universe really has a hidden direction, what is it pointing toward? To understand why this is so strange, we need to go back almost 13.8 billion years, not to the beginning itself, but to the moment when the universe became transparent. In its earliest phase, the universe was hot, dense, and filled with charged particles. Light existed, but it couldn't travel freely. It was constantly scattered. Then, as the universe expanded and cooled, atoms began to form. Suddenly, light could move through space. That ancient light is still around us today. But because the universe has expanded for billions of years, that light has been stretched into microwaves. We call it the cosmic microwave background, or CMB. Think of it as the oldest visible surface of the universe. Not a photograph of stars, not a picture of galaxies, but a snapshot of the universe when it was only about 380 years old. To the human eye, it would look almost perfectly smooth. But with sensitive instruments, scientists can detect tiny temperature differences, small fluctuations that later became the seeds of galaxies, clusters, and everything we see today. And that is where the mystery begins, because these fluctuations are supposed to be random. Not perfectly random in the casual sense, but statistically random according to our best cosmological models. There should be no giant cosmic arrow, no preferred side, no hidden pattern that seems to organize the universe on the largest scales. But when scientists studied the CMB in detail, they found hints that something might not be quite right. NASA's WMAP mission, and later the European Space Agency's Planck satellite, gave scientists some of the most detailed maps of the cosmic microwave background ever made. These maps became one of the strongest pieces of evidence for the standard model of cosmology. In many ways, they confirmed what scientists expected. The universe looked flat on large scales. The early fluctuations matched many predictions. The basic picture of cosmic evolution seemed incredibly successful, but hidden inside that success were anomalies, small at first, easy to dismiss, but persistent. Some of the largest scale patterns in the CMB did not look as random as expected. In particular, scientists studied something called multipoles, mathematical patterns that describe temperature variations across the sky. The lowest multipoles correspond to the largest structures in the CMB map, and that's where the trouble appeared. Two of these large-scale patterns, called the quadrupole and octupole, seem to be unusually aligned. Instead of pointing in random directions, they appeared to share a preferred orientation. This was not what the simplest version of the cosmological model expected. It was strange enough that researchers began to ask whether the map was revealing something real or whether something had gone wrong in the measurement. And that uncomfortable alignment became known as the axis of evil. The name was dramatic, maybe too dramatic. But the question behind it was serious. Why would the largest patterns in the universe seem to point in a similar direction? The axis of evil is not dangerous because it means something supernatural. It is dangerous because it challenges a basic idea called the cosmological principle. This principle says that, on very large scales, the universe should be homogeneous and isotropic. Homogeneous means that matter is spread out in roughly the same way everywhere. Isotropic means the universe looks roughly the same in every direction. This does not mean every galaxy is identical. It means that once you zoom out far enough, there should be no special direction in space, no cosmic north, no cosmic south, no preferred axis. The cosmological principle is one of the foundations of modern cosmology. It allows scientists to build models of the universe without placing Earth, the Milky Way, or any direction in a special position. But if the axis of evil is real, then maybe the universe is not perfectly isotropic. Maybe something about the early universe created a preferred direction, or maybe the data is being affected by something closer to us. That is why this mystery has survived for so long, because every possible explanation leads somewhere uncomfortable. If it's real, cosmology may need revision. If it's not real, we need to understand why our maps keep showing it. And if it's contamination, then one of our most important windows into the early universe is harder to clean than we thought. But the axis of evil is not the only strange feature in the CMB. There is also the famous cold spot. In one region of the sky, scientists found an unusually large area that appears colder than expected. Not cold like empty space, cold compared to the tiny temperature variations in the cosmic microwave background. At first, it might sound like a small detail, but in cosmology, small details matter. A temperature difference in the CMB can represent information about the early universe, the distribution of matter, and the way light traveled across billions of years. The cold spot became one of the most discussed anomalies because it seemed unusually large and unusually cold. Some scientists suggested it might be caused by a giant supervoid, a huge region of space with fewer galaxies than average. As CMB photons travel through such an underdense region, their energy can be affected in subtle ways. But the explanation is still debated. Some studies argued that a supervoid could explain at least part of the signal. Others found that it might not be enough, and that is what makes the cold spot so interesting. It sits at the edge between two possibilities. Maybe it is a rare but natural statistical fluctuation, or maybe it is a clue that the universe contains structures or effects we still don't fully understand. At this point, the biggest question becomes simple. How many anomalies can we find before coincidence starts to feel uncomfortable? One strange alignment might be nothing. One cold region might be a statistical accident. One asymmetry might be caused by foreground contamination, but when several unusual features appear in the same ancient map, scientists have to ask whether they are connected. This is where the mystery becomes difficult, because the universe is enormous, and when you search through enough data, strange patterns will appear. Humans are also very good at seeing patterns, sometimes too good. We see faces in clouds, shapes in stars, meaning in randomness. Science has to be careful not to turn noise into a story. That is why many cosmologists remain cautious about the axis of evil and other CMB anomalies. Some analyses suggest that, after accounting for foregrounds, masking, and secondary effects, several of these anomalies become less statistically significant. In other words, the universe may not be pointing anywhere at all. The axis might be a combination of chance, data processing, and the difficulty of observing the entire sky from inside a galaxy. But the fact that the discussion continues tells us something important. The anomaly is not easy to dismiss completely. And even if it turns out to be a statistical illusion, it teaches us how fragile our understanding can be when we look at the universe on the largest possible scales. There is another reason this mystery is so hard. We are not observing the universe from outside. We are inside a galaxy. The Milky Way surrounds us with stars, dust, gas, magnetic fields, and radiation. When scientists map the cosmic microwave background, they must subtract the foreground signals from our own galaxy. That sounds simple. It is not. Imagine trying to hear a whisper from the beginning of time while standing inside a noisy machine. That is what CMB cosmology is like. The signal scientists want is incredibly faint. The foregrounds are complex, the instruments are not perfect. The sky must be masked, cleaned, corrected, and reconstructed. Every step can introduce uncertainty. So when a strange alignment appears in the cleaned map, scientists have to ask, is this pattern really from the early universe? Or did something closer to us create the illusion? Maybe it is galactic dust. Maybe it is scanning geometry. Maybe it is how the map was processed. Or maybe it is real. That is the frustrating part. The cosmic microwave background is one of the most powerful tools in all of science. But it is also one of the hardest signals to interpret perfectly. And when the possible anomaly is on the largest scales of all, we only get one universe to observe. We cannot run the Big Bang again. We cannot take a second universe and compare it. We only have this sky. And this sky has a few strange features. So what if the axis of evil is not an illusion? What if the universe really does have a preferred direction? Several ideas have been proposed. Maybe the early universe was not perfectly isotropic. Maybe cosmic inflation, the rapid expansion believed to have occurred in the early universe, left behind subtle directional traces. Maybe the universe has a shape or topology more complex than we assume. Maybe we live in a region influenced by physics beyond the standard model. Or maybe the anomaly is connected to something even deeper. The possibility that the observable universe is only a small patch of something larger. This does not mean there is a wall at the edge of space. It does not mean there is a center of the universe. But it raises a powerful idea. The part of the universe we can see may not be enough to explain all the patterns we observe. If the observable universe is like a small window, then some strange alignments might be hints of a larger structure beyond that window. That idea remains speculative, but it is exactly the kind of question that makes cosmology so fascinating, because the largest mysteries are not always about things we can see. Sometimes they are about the assumptions we didn't realize we were making. The axis of evil matters because it forces science to test itself. It asks, are our models describing the universe correctly? Are our observations clean enough? Are we mistaking randomness for meaning? Or are we seeing the first faint signs that the universe is stranger than our equations expected? This is the line where real science becomes more interesting than fiction, not because scientists are terrified in a Hollywood sense, but because the universe can still surprise the people who understand it best. The cosmic microwave background was supposed to be a map of the early universe. Instead, it became something more, a mirror. It shows us not only where galaxies came from, but where our assumptions may begin to crack. And that is why the idea of a hidden cosmic direction is so powerful. It is not just a mystery about space, it is a mystery about certainty. How much do we really know when our entire picture of the universe comes from one observable patch? Maybe the axis of evil is nothing more than a statistical coincidence. Maybe future data will explain it away. Maybe the cold spot is just a rare fluctuation, and the strange alignments are artifacts of how we observe the sky. That is possible, but maybe not. Maybe the universe still carries scars from its earliest moments. Maybe those scars are stretched across the sky in patterns so large that we are only beginning to notice them. And maybe, hidden inside the oldest light in existence, there is a message that does not say where the universe began, but how little of it we truly understand. For now, the question remains open. Does the universe really have no preferred direction? Or is there, somewhere in the ancient light, a hidden axis pointing towards something we have not yet discovered? Because if the universe has a direction, then the next question is even stranger. What lies at the end of it?